do, well, code anyway. Um, so today we're going to be talking about Golang channels, and unlike a lot of the other classes that I've kind of been giving over the last few weeks, this time I'm not coming with pre-prepared code. We're going to write this live, um, purely because it's a little bit more fun that way. I'll be asking people who are on the stream, etc., to give me any indication of what they think I should be writing here, and we're going to write some stuff that's going to use concurrency. But before I get into that, any questions about the stuff from last week where we covered pointers? Anybody done any work on the stuff? Um, Anything else? Just before we get going with this, I'd like to get some feedback on everything that's happened up till now. I'd also encourage people, by the way, on the Zoom chat to please use your microphones, because obviously that way it's heard by the people on the Facebook and the YouTube streams, whereas the text comments aren't necessarily heard by everybody. So, any comments, feedback, anything else before we get started?
Yeah, Andrew, one question. The GitHub repository. So we used to. There are two methods. One is star int. Another one is star uint. Another one is uint ptr. So what is the difference between these two methods?
Okay, is this in the pointers file?
Yeah, that's right. Pointers file.
Okay, so let's take a look at that. Okay, so oh, I'm getting a lot of feedback from somebody here. I think just mute the mics if you're not talking, and that way, just unmute when you are. But okay, so to look at this, if you're looking at this pointer no return, for example, where I have an int and then I've got a star int, the big difference here is that this here is passing actual data, whereas the star int as an argument passes a pointer to that data. So effectively, you're passing the location of the data. This is why when I pass in A and B over here, and I multiply those and I put them into this result, which is defined as C star int, and you can see also star C over here, I'm storing that in the location of C. So I don't need to return anything because it's being stored at a location that is known by the calling function. Now, with regards to you'll see you mentioned int and uint16, and there are uint8, uint32. Basically, every number, if you go back to the original stuff that I talked about with regards to binary, numbers are made up of zeros and ones. And the more zeros and ones in the sequence, the larger the number can get. So an 8-bit number, for example, equates to 2 to the power of 8 as a maximum decimal number. Whereas with a 32-bit number, it's 2 to the power of 32, 16-bit number, 2 to the 16, etc. So a UN16 can hold a maximum value of 0 to 65535. A byte, which is a uint8, can hold 0 to 255. A uint also means that it's an unsigned integer, which means that it's always 0 or greater than. It can never be a negative, whereas an int can go negative and positive because some of the bits are used for negative and positive on the number. Does that answer your question?
Yeah. So my question is around, this return byte in this function, in the return statement at the end we have uint ptr, and there is another function, another method called star uint.
Okay,
So in the
let me
uint
find
ptr.
that. Okay, so that there, right, is purely, let me just see, where did I use the uint pointer?
Yeah, I did
Yeah,
not find it here, like in.
yeah, no, I do see it here. I don't think it's defined in my local copy. Oh, sorry. So uint pointer, right, is a built-in Golang pointer. And effectively, that takes an unsafe pointer and it makes a integer version of that pointer. The reason for doing that, so unsafe pointer right over here with a reference to A is going to return me a pointer value. The thing is, in Golang, as kind of a safety mechanism, what you can't do with a normal pointer produced by unsafe pointer or by a reference, etc., is to add or subtract from it. Whereas in this particular case, what I'm doing is I'm converting that pointer to a normal kind of integer. Then I'm adding to that and then converting it back to a pointer to get to a memory location. So effectively, I can iterate through memory by simply adding to the pointer and increasing or decreasing my location in the memory. Does that make sense?
Yeah, got it. So event PTR is basically converting the hexadecimal pointer to a integer. Yeah.
Yes.
Okay. Okay.
Okay. Any other questions, etc., before we continue? Okay. So today we're going to be talking about Golang channels and concurrency. One of the major advantages that you find in the Golang language, and it's one of the reasons why, talking to people who use Golang like I do, as to why do you use Golang over something else? And it's got to do with how easy Golang has made it to write code that can run concurrently, basically threaded code. Now, technically, Go uses something called a Go routine, which for various reasons isn't quite a thread, but you can almost consider it like a thread. And effectively, it allows you to launch multiple routines simultaneously. And I'm going to demonstrate that quickly we're going to make a small function here called, we'll call it func print something. And we'll make it print for I colon equals 0, I is less than 100, I plus plus, format dot printf %d slash n comma I. And that function there, if I were to run that function normally, so let me just open this window here. In fact, I think I'm going to split this window. And let me do this in terminal. And if I take this, and let's see if it's going to let me dock this. So there we go. Now we can see it side by side nicely. If I do a go run channels go to run it, it's printing 0 through 99. In fact, I'm just going to make this slightly smaller because it'll. Okay, so I'm printing 19 numbers. Now, if I were to do something like this, so now I'm going to fire 5 routines at the same time. What Go does as a statement before the function name is say, start this almost as a thread in the background, and it's going to run. But the problem with doing this in the main function is that basically the program's going to exit once it gets to the end there because everything's going to be backgrounded. So what I typically do here when I'm demonstrating this is simply put a pause in this. Just make it wait 1 second before it just quits on me. And if I run this now, you can see I don't think I'm really running this for kind of long enough to see the full effect of the threads, but effectively it's running all of this. You can see over here, Occasionally you'll see two numbers that'll appear right after each other, etc. The reason for that is because this stuff is executing concurrently. They're not executing separately. And the even better way to kind of demonstrate this is if I were to make this print 200 numbers, and we'll print them with a space after them each time. And hopefully we've got enough numbers to, because the computer typically finishes the stuff so fast that it can be quite difficult to see. But what you start seeing is you start seeing overlapping numbers in certain places in the print. And the reason for that is, as I say, you're not running these things individually. They are literally running at the same time. Um, and another way that you can kind of demonstrate this is if I were to, so in Golang, let me cover another couple of concepts before we move too much further. When you run a Go routine or a thread, you need to be able to get data back from that, and you can do that via channels, which I'll talk about in a bit. You also need to know when a thread has finished, which you can do using something called a wait group, which basically allows you to pass a pointer into the function, which you can use to signal before your function ends. And I'll show you how to do that in a second. We'll also talk a little bit about mutexes in a short while. But if I were to do something like this, and what I'm going to do here is I'm going to make this pause 1 second before it exits as well. And so this WG line is effectively creating a mutex. Sorry, this should actually be sync.wait group. That just basically creates a wait group that will basically make the compiler wait for something when I tell it to. And we do that by, I'm going to be starting 5 routines here. So if I do a wait group add 5, and at the end of this, I tell it to wait group wait. What that says is create this thing called add, start the 5 functions, and wait until they're all finished. And then at the bottom of the function itself, I tell it wait group done. So what's actually happening here? And I'm going to pass the wait group in here. There we go. So this here says I'm about to run 5 threads. This here passes something into the function that allows the function to signal when it's done. Every time one of these functions calls done, this 5 basically decrements, and you get 5, 4, 3, 2, 1 until you get to 0. This wait group wait says, do not do anything until all the functions are finished. And if I run this now, and we'll put in a print statement here quickly that says, and if I run this now, you can see there was that brief pause, and then all the functions returned at the same time because they're all doing the same thing. If I were to make this thing do something slightly more CPU intensive to make it take longer, so I could, for example, import math.rand, which is going to produce some random numbers, and we'll make it produce a lot of random numbers. And we'll do something like for x colon equals x equals math, rand dot int, and we'll put a start time function in here as well. So if we do this, start time is duration. So let's go back there. And I'll expose that quickly. So effectively, what I'm now telling it is that it's going to tell me, I can actually put a start time in here as well. Started at %s. So what this thing is now telling, and I'm going to make this number nice and long and huge so that it takes a little while, hopefully. This is basically going to cycle through producing random numbers, a load of them. And when it's done, it's going to tell me what time it finished and how long it took, right? And if I were to run this now, whoops, I've made a mistake there. Var x equals 0, x equals, okay. Need to actually use the variable because at the moment I'm just setting it, I'm not using it, it doesn't like that. Last random number colon percent %dx. And if I run this now, you can see that all of these things here started at almost exactly the same time. Now, I don't know how long this is going to take. I may need to cut down on the numbers that I'm generating here because that's kind of a huge number. So let me restart this. And at the moment, so that's what you'll see here is that all of these functions, right, started literally nanoseconds. Well, it's probably milliseconds, nanoseconds apart. And all of them ended at practically the same time with practically the same duration or very, very close. And you can see that they all ended at the same time. Why they do that? Because I'm running them concurrently. Does this make sense to everybody?
Yes, it's very clear.
Any questions about this? Because I'm sure you can see the practical applications of this. If you're, for example, automating something in a DevOps environment and you want to go and execute a command on 1,000 devices, you can write a function that takes your input in arguments and tell this function, I want to run 1,000 copies of you at the same time and fill in the arguments as I fire the things, and then wait for you guys to come back, and then you've completed all 1,000 tasks at the same time. So you're no longer working in a world of sequential code. That makes sense.
Yeah, makes sense, Andrew.
Now,
Makes a lot of sense, Andrew.
so now what I'm going to show you next is the use of channels, right? Because the thing is, once you start a Go routine or a thread, you need to be able to put data into that thread and take data out of that thread, because otherwise it's running in kind of a black box. So Golang has this concept of channels, and basically imagine a pipe where you can put something in one end and it's going to pop out at the other. So you put something in at function A, it pops out in thread B or C or D or whatever it is, right? And the best way to demonstrate this is if I were to go and make, for example, we do something like this. X colon equals byte 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. So I've got this random slice of bytes, right? And let me get rid of my weight groups here. Then I'm going to make a channel over here called demo channel, and we're going to make this in fact, we'll make it a Boolean channel. And actually, no, let's make it something more interesting than that. We'll make it a byte. Yeah, byte channel's fine. And I'm going to change this slightly to get rid of the weight group. And into this function this time, we're going to pass our channel called demo_chan, which is of type channel byte, right? And what we're going to say here is I'm going to change this routine here, and I'm going to say something to this effect. For, because I don't want this thing to just exit. So I'm going to put this thing into a loop, right? And then I'm going to use a statement called select, which basically says, wait until I get input from something. And I'm going to say input colon equals, and this is where the syntax gets a little interesting. It becomes a case statement. So, like so. And basically what that statement says is start this for loop and keep going through this for loop until I get input from this thing called demo_chan. And at that point, I can do something interesting with it, and I can go format.printf got input from channel %d input. And then I can also do something to this effect where I say if input is equal to 255 return, which basically says if I send down 255 down the channel, then it's just going to quit the routine, right? So now I take this little array of mine, and I'll get rid of all of this, and I'll go for I range X. So basically I'm now going to iterate through this array, and I'm going to say go print something. That's going to start all my Go routines, and I'm going to pass my channel into my Go routine. So at this point, I've now got a bunch of routines that are waiting for me. And what I'm going to do in here as well is I'm going to make this thing go to sleep for the duration of the number that's been passed in there. Just turn that into a duration. So now effectively what this thing is saying is get this random number that I'm about to send in here, go to sleep. Once it's finished sleeping, print something, and if I happen to send it 255, quit. Now, I actually want to change this and put this up here because otherwise I'm going to be sleeping when I actually try and quit the thing. Then I'm going to take this thing and I'm going to effectively send this thing. In fact, your even better way, yeah, let's do it this way first. So I range through X again, and I go input, demo_chan, which is the channel that I passed it, and I'm going to send it I, which is what is in X. And in fact, I can just change this. So effectively, I'm ranging through X. I'm starting the routines. Once they've all started, I range through X again, and I send those values into the function, right? Once I've done that, I can now tell this thing I'm going to go to sleep for a while. Let's make it 30 seconds. 30 times time dot second. Just to go to sleep. So if you watch what happens when I run this now. Oh, I've still got an error in there. Let me just check what that is. Ah, just leftovers from the previous code, the imports. And one other one. I can actually just do that. There we go. So when I run this now, in fact, I'm actually going to also just print that I'm starting thread %d, I. And so it'll tell me as it starts each thread. And then over here, I'm going to print that I got a return from a thread. Got return from thread. Sorry, this is where I'm sending into thread. Sending into thread. And let's see what happens here. So you can see now that the threads are waiting a second each because each thread is waiting for the input that I gave it number of seconds. That's why you're seeing them come back 1 second apart like that, because of the sleep in this function here. If I were to take this sleep function out here, what you'd see is that almost instantly I get all the input, and now it's just waiting to end, right? So effectively that is injecting data into a thread, and those threads are still sitting there running until my program times out and ends, right? Does that make sense to everybody what I did there? And I'll explain. I saw a question, Matthew. If you can just ask you to ask that question on the microphone rather than in the chat, so that it can be heard on Facebook and YouTube streams as well, please.
Oh, sure. No, it was just a quick one. Wally, I didn't want to disturb really because that underscore there in the for statement, I didn't quite get how you.
Okay. So the underscore basically is almost like, for the Unix guys among you, consider that dev null almost. It's effectively saying, I need a placeholder for something that's returning from a function call or something else. That underscore basically means get it and throw it away. Because on a range statement like this, if I do for x comma I, for example, so I would have changed this to be something like that. What that would do is fill in x with the offset of my slice. I would be the value of my slice. But since for the purposes of this function, I don't need to know the offset, I only need the values to send in, I put the underscore in there and the data disappears. It just gets thrown away. Does that make sense?
Okay, basically it can be anything.
Yeah, that underscore is basically a throw this away. It literally means throw it away. So yeah.
Okay, cool.
But does the concurrency that I've explained here kind of make sense? Because before I continue and get more complicated, I want to be sure that I haven't lost anybody here. Okay, I'm going to assume that you guys then get this. What happens now if I want to get data back from this function? So I'm going to change this slightly to say input and output. So I'm now passing in two variables here, an input channel and an output channel. This over here is going to, we'll just change the name of what I'm putting it in, and we're going to get data from input. We'll leave the input 255, then quit. And we'll say something like output in times 10. So now what this is saying is get a number from my input channel, multiply it by 10, and send it back out of the output channel. So now if I go in here and I say the same thing and it's sending in the number, demo channel going into I over there, we create a return channel, and once I've sent in all of this data in here, I can then go for I colon equals 0. Actually, I can just do a range on X, it's the same length. For range X, and I don't even need this anymore. So what this is now going to do is it's going to send in a bunch of numbers into this thread that's sitting over here. And then, in fact, I can just make this a single thread because I don't actually need to start multiple of them. And I need to pass it the return channel. So effectively now what I'm saying is start a thread that's got these two channels, an input and an output. Then send into that channel all of these numbers over here, then go through and expect the same number because it's the same length in the range, and pull my return channel to get that return data and print it out. So what will happen here now is that if I run this, I need to put a pause in here. 10 times time dot second. Just make it pause there. Let me just have a look. What am I doing wrong here? So basically what this thing is now saying is that all my channels, all my Go routines are basically, they went to sleep. And so nothing's actually running and it doesn't like that. So kind of, die the moment it does that. And I just want to see where I've gone wrong there. Send it into I. Just see. Okay. I think I might actually need to start a bunch of channel. There we go. Let's just do that. And there come back all the numbers. Sorry, I didn't start the right number of threads. But effectively what happens here is I'm shoving this number into this channel. It gets the number, it shoves it back out to me, and I print the return channel. The other interesting thing about this is that if I take out that pause now, before, I need to take out that. Before, this thing would have quit automatically because it's running a thread and it's not waiting for anything. Here's the thing. When I read for the return on a channel, by default, it will block, which means that if I tell it read from a channel and there's nothing coming in on that channel, the program will not continue until such time as it gets something from that channel. That can be a little tricky at times because if I, for example, change this, we know that I've got 10 returns coming back. And if I were to do something like this, I is less than, say, 15 I plus plus. So now what I'm saying is I want 15 returns, but I'm only getting 10 because of what I've sent in there. And I'm going to print done when I'm done. what'll actually happen here when I run this? Anybody want to take a guess as what's going to happen? Anybody?
It might not finish because you have 10 and you're waiting for 50.
Exactly. It's effectively going to get stuck, as you will see. Let me just see. It actually deadlocked there. It effectively says all your routines are, if I take this out over here, that should actually solve it. It basically, it really doesn't like that because it's effectively saying, listen, yeah, I can't do this. There's not enough input. I'm stuck, right? So you've got to be a little careful about when you read from channels, when you're getting back from channels, etc., etc., etc. They are very, very, very useful things, though. And you use them when you're doing things like reading from network sockets or doing any form of parallel functions where you need to get a whole bunch of data back. So I could, for example, do something to this effect. Number colon equals rand dot int 31n, and we'll say it's a random number with a maximum value of 2 million. And we'll add another 200,000 to that to make it kind of a minimum number. Now, if I were to do something to this effect, and we'll take out the input number, so we've just got an output number here, and I go for I colon equals 0, I is less than whatever the random number is, I plus plus, and I then tell this thing, so now I've got a completely random block of numbers, and I'm going to tell this thing that I want to produce a random number that many times, and when I'm done with that, I will then pass an output variable, and we'll say it'll be, let's make it like that, y. So effectively, this thing is going to now, let me just see what is it not liking there? So this int31n, by the way, in the random function that I'm using here, produces an int32 rather than an int. So I have to actually tell it that they're the same number type. So if I just do this, that'll clear my error because now I can actually compare them. They're now the same type. And then because I'm passing an integer back into the channel, this channel has to be of the same type again. So effectively what I'm saying here is pick a random number, then iterate through that number, and each time you do, generate a kind of a random integer, and the better way to do this is actually var y int, and change this so that it's going to run through this loop. When it's done with the loop, it's going to pass me the output of whatever the last random number that it generated is. That means this function is going to kind of run for a completely variable amount of time. We're still going to use our return channel, and we're not going to pass anything in, so we'll get rid of that. For I colon equals 0, I is less than 10, I plus plus, go print something, return channel. So that's going to fire up effectively my 10 routines. And now that I know that I'm waiting for 10 returns, 0, I is less than 10, I plus plus, and I'm going to go Z colon equals return channel and format dot print dot return %d %d I comma Z. And basically what that's now saying is start 10 of these functions, which are going to do this random iteration. Then wait for the 10 returns. As I get the returns, print them out, right? And I can also tell this thing to quit the thread when it's done because I won't need it anymore after that. And if I run this, you can see there that I start getting random numbers back. They were all generated concurrently, but the difference in the time is because of this amount over here. And what you'll see over here is that if I tell this that I'm going to put in I'm going to pass in a thread number over here, and I'm going to say something like returning from thread %d tnum. So it's going to print out when it returns which the thread number is, and I'm going to pass in the iterator over here where I'm starting the thread into there. So effectively what this is saying now is tell this function what thread number you are. It's going to print that when it gives me my output. Then it's going to give me my output, which I'm going to print over here. And what you'll see here when I run this now is that these numbers here are, I'm just trying to see, you'll see that they're not in sequence. Because they were all running concurrently and they're having to do different amounts of work. So thread 2 finished before thread 0 did. Thread 5 finished, after thread 0 and 2, etc., etc. Does that all make sense? Any questions on this so far?
Andrew, I have one query.
Yes.
What is the difference between return and the output keyword? Both are same.
Okay, so the output over here is sending data, right, down the output channel, which I'm getting over here. This return here is basically just saying return from the thread and quit the thread. It basically just exits the thread because once I've sent it that output, I don't need the thread to hang around. So that just quits the thread, the return. It's not actually returning any data. It's just basically exiting the thread. The actual output is coming from this line over here.
Thank you.
Any other questions before we continue? Because then I've got a question for you guys, and I'm going to need someone to think about this to answer me because I want you guys to, in the spirit of participation, actually think about this question. If you consider the work that we were doing with pointers last week, in conjunction with this concurrency, what are the issues that you can see? Do you see any problems with this?
Yeah, if the shared variables are there.
You could effectively end up with two threads that are running concurrently, changing the same area of memory at the same time. And that means that if one is reading it and the other is writing it, what the guy is reading becomes undetermined because something could change it as he's reading it. And that's going to cause a problem, right? That is one of the biggest issues that you can hit with threads is when you get what's called a race condition. And that there can be demonstrated most easily by if I take this thing and I pass in another variable completely. So this time I'm going to pass in an integer and I'm going to call it x, right? And instead of using y, I'm going to say star x equals rand. And then I'm going to pass star x out over here. And what I'm going to do is take exactly the same function again, right? And this time I'm going to pass in z colon equals I, just make another integer so that I've got something to pass in there. And I'm going to pass in a pointer to z. So these functions are all getting this random thing in. And they're all going to try and change it at exactly the same time, right? And what you'll see here is that that still looks okay when it's running like that. But Golang has this thing called a data race detector. So if I were to rebuild this, and so now I've built it with race detection on, and I run it, and hopefully what you should see, it's thinking about it. It's actually quite surprising. Let's do this. See if I can trigger a race. It's can be quite challenging actually to trigger races when you want them. Otherwise, I'll do this with a slice, and you'll see it better on a slice potentially. Where if I were to do something like this, so if I were to do z colon equals make map. So that's just making me a map. Now, the thing about Golang and maps, and I'll talk about these in a second, is that I happen to know, because it's in the spec, that maps are not what are called thread safe. So I'm going to fill this map with a bunch of data, 0 colon for I colon. We'll fill it with like 5 million numbers. And zi equals true. So all that's basically doing is now filling in that map. So I've got some data in my map, and now I'm going to change this thing such that I have an input over here which is of a map. So in map UN32 bool. So I've got this map coming into my thread, right? Now, if I tell this thing over here that I'm going to rerun this thing so that I'm going for I colon equals 0, I is less than 5, 1, 2, 3, I plus plus, in I equals I. And so now I'm going to change that map, and at the same time, I'm going to tell it that I want to print out what is in that map at the same time, right? So I'll do something like comma in I. And then I'm just going to pass 0 as an output over here. So now what I've got in this particular instance is that, let me just make sure that okay, this needs to be a UN32. So now I've got this map type variable where I'm changing it and reading it at the same time, right? And what you'll see when I run this, hopefully if the demonstration works as I'm kind of hoping it will, let me just do this. And let me just make sure that I took out my thread number here. And go print something. And I'm going to pass that in my map. I'm going to pass that in my thread number. And I'm going to pass that in my return channel, which is over here. So now I've got these 10 functions that are effectively going to be trying to read and write from this map all at the same time, right? Now, that there is, sorry, I forgot to put int over here. Yeah. There we go. I just want to see, have I got an error here? So I've got this code that's going to be firing these 10 routines, and all 10 of them at the same time are going to be trying to read and write from that map, which I know is not thread safe. And just to make this more interesting, I'm going to make this 1,000 threads so that there's going to be overlap, hopefully, as a demonstration. And if I go and run this now, what you see here, go run, is an instant massive crash. And why is it crashing here? Because what it's saying to me here is that I'm trying to read and write from the same thing. I'm going to try and reduce this to 10 so that I don't get as many crash messages, so that it's easier to get to the base crash message. There we go. So you'll see here that this thing is basically giving me a ton of errors. And the reason that it's doing that, when I scroll all the way up here, let me scroll up, you'll see that I've got a fatal error because of concurrent map writes. Basically means that two things tried to change this map at exactly the same time, and it didn't like it. Does that make sense? Because I'm changing the same memory from two places at the same time, the thing's not going to know what to do with it. Does that make sense?
Yes, now I think the mutual redistribution cases of routing protocols makes a lot of sense to me as to what might have happened with the entire routing loops and the race conditions there.
Yeah, you've got to be quite careful with this, but there are ways of solving this. Because if you remember, I used something called a wait group earlier to wait for things to return. There is another part of the sync package called a mutex. So if I do this, so that is going to create me a thing called a mutex, right? And I'm going to pass that mutex in over here as yet another parameter. And I'm going to pass it in over here. Let me just see. Oh, need to create a pointer. So now I've got this thing called a mutex that's going into this function, right? What I'm going to do over here is, and I'm actually going to make this just so that we don't spam everything. I'm going to tell this thing to do a m.lock. And when I'm done, I'm going to tell it to do an m.unlock. What this thing is now telling me is that it wants it to take control and tell everything, listen, I'm going to be reading and writing from this thing. Do not touch it. Stop and wait. And it basically enforces a wait on everything else. So it's going to lock down the calling function and all the other Go routines until it's finished its read and write. And if this is behaving correctly, when I run this time, you'll see no crash. No crash because I've locked the code. So it performs a lock, does its thing, and releases the lock. That makes sense to everybody. before I show you the issue with mutex locks. Any questions? Anybody? Okay, so here's the thing about locks. If I tell the thing to lock and I don't tell it to unlock, and then from another function I tell it to lock again, remember that the other function is going to be waiting for that lock. What's going to happen is that I'm going to end up blocking all the functions that are waiting for the lock. So you've got to be very careful that when you lock something, you remember to unlock it, because otherwise you can create a deadlock in the program and everything stops functioning. Does that make sense?
Yeah.
And I'll show you what happens here, because if I do this, and remember that lock is not function specific because it's a pointer, right? So it's going to apply to all of them. If I run this over here now, I'm locking, then I'm doing this stuff, and I'm returning some output, right? So what's going to happen when I run this is I'm going to get one output. The rest of it is going to be stalled. If it doesn't crash like that, yeah, it actually crashed because it really didn't like that. Let me just run that again so I can see what those crash messages are. Basically, you have to get your locks right. Threading and concurrency and pointers can be tricky. They're also some of the most useful aspects, though, of Golang and code in general, because you want to be able to do things in parallel. Remember, if you go and buy a modern day CPU, so if you buy an i9 CPU, you can have up to 14 cores on that thing. In my case, I'm running an AMD Threadripper 3970, so I've got 32 cores in this machine. If I don't implement Go routines, no matter what the PC is doing, it's only ever going to eat one CPU, because without the threading, it's going to lock all of that to one CPU and it's not going to cross the CPUs, and I'm going to get fractional utilization out of my resource. This is why we thread. And here's the thing. If you look at some of the other languages, so if you look at C, you can do threading in C using what's called POSIX threading. It's complicated. It's very complicated to write proper threaded code in C. If you look at Python, Python can also thread, but Python uses what's called a global lock. So if you take Python and you tell it to do 10,000 things at the same time, and then you watch your CPU, you'll notice that your machine's never going to eat more than 2-3 CPU cores at once. Because what Python is doing to protect itself is locking everything so that everything is actually running almost sequentially. And while it might look like it's running in parallel, you're never going to get true concurrency because of what is known as global lock in Python. This is the thing that has driven so many people to Golang when they're doing computationally heavy work that needs that multi-threading. Because the only way to achieve that in a language like Python is to go with multi-process, which you can also do. And that effectively starts entirely new processes, but then you also don't have the channels. So you have to start using a method of data exchange in Python that uses something called pickle. Pickle effectively serializes your data before it sends it back to you and is very, very, very slow doing it. Whereas with channels, I can shove data in, I can shove data out, I can do it all concurrently, and it all just works. Does that make sense? Well, what I'm going to do is I'm going to divert away from the training code for a second. I'm going to show you some real code that I wrote. Oops, I will bring that back up in a second for another project that'll demonstrate this slightly better. Let me close off a bunch of things here. This is one of these programs I was working on that's got rather a lot of files involved. So if I look at something like my FSM function in here, this code is actually part of a BGP daemon. So this is it's a full BGP daemon. And what I've got in here, if I scroll down to my reader, this is where I'm reading the data kind of off the network. So this function over here, effectively down here, you will see over here, it's running in a for loop. So this is a constant loop, and it's polling my network card for data. Give me data, give me data, give me data. When it gets that data in there, if it gets an error, it signals to my monitor routine, listen, this socket has got an error. Close it down, make it go away. At the same time, if it gets legitimate data over here, take the data it got off the network card and send it to another thread that processes that data while it waits for the next piece of data. So effectively, I can have 500 TCP sockets that are all reading data off the network on a constant basis. As they're getting it, they're shoving it off to a completely separate processor that is in turn going to process it while this thing keeps reading my socket uninterrupted. Does that make sense? Because if you want to get the best out of Golang, knowing about these channels and this concurrency is absolutely critical. What I would say is that before we start writing practical application code next week, I really would encourage you guys to spend a bit of time playing with these channels. The syntax for channels themselves, let me go back to the other code. The syntax for channels, which I was demonstrating here, is actually really, really simple because you've got to make the channel first. So you make a channel simply like that. Make chan int, make chan uint, byte, whatever. So this effectively makes a channel of a particular type. Over here, when I'm saying variable colon equals and then this syntax over here, which is just a greater than hyphen combination, and then the name of the channel, that says read from the channel and put the result into the variable specified. If I want to send into a channel, then I use the syntax here where it's my channel name, and then I use my that's less than hyphen, and then whatever I'm sending into the channel, and that sends it in and out. So you can receive and you can send. And don't forget that you've got to actually make your channel, because if you don't make your channel, you're going to basically be sending the data into the ether, and it's never going to get anywhere. Before I continue with the next little piece, any questions about this? Nobody? Okay. The next thing I want to talk about, right, is with these channels, you have things called buffered channels. Now, what a buffered channel does is it allows you to send in multiple inputs into it before it starts blocking. And it effectively creates this kind of backlog When the buffer's full, until the buffer gets cleared, the routine starts to block again. I don't use a lot of buffer channels, but what I do use them for is kind of thread scheduling. So let me show you it like this. If I take this function here, it's going to delete all of this, and I'm going to make this an input this time, and I'm going to make it a Boolean type because I'm not going to need a lot. And in this particular case, the very first thing that I'm going to do is read from this Boolean channel, right? Then I'm going to tell this thing that I want to run, I don't know, 2 million iterations, and I'm going to go equals math.ran int. So go and make 2 million random numbers. Put that right thing over there. So, and then, so effectively what this thing is now doing is saying, read from this channel before I start, and it will block before it does that, right? I'm also going to tell this thing that I want this thing to, in fact, even better. What I'll do is I'm going to put something into the channel first, right? Then I'm going to sleep for a random amount of time. Let's see if I can find something small enough. Let's sleep for 10 seconds. And then when I'm done, I'm going to tell this thing that I want to clear my buffer channel, right? And I'm also going to add it a return channel just so that we can see what it's doing. And I'm going to make that a integer channel. And I'm going to push my last, let's just see, rand.int. So I'm going to push a number to the return process, and then I'm going to clear my channel, and this function will exit. So what's the point of doing this, right? If I now go and I make this random channel that I'm going to use for blocking routines, and I do something like this, sigchan, which is my signal channel, make chan bool, comma 2. That says I've got a maximum buffer here of 2, right? What will happen here when I call this routine now, and I need a return channel, redchan, makechan, int. And I tell this thing that I'm going to go and start 10 of these things. Sigchan, redchan. So I've got my signal channel going in there, and I've got my return channel. And then over here, I'm going to read from my return channel to print it out again. So if you look at what this does, it's going to start all of these functions at the same time, all 10 of them, except the first 2 that start are going to shove something into input. Because it's going to accept those, because remember, it's a buffered channel, it will then continue because it doesn't need to wait to get space in the queue on the channel. And when they're done, it'll clear its buffer point on the channel. However, the following 8 are going to have to queue to wait for slots on their channel. So what you'll get here is that the first 2 functions will run in parallel. As they finish, the rest will fire one after another, always making sure that you've only got 2 running because the others are blocked. Does that make sense?
Yes, yeah.
So effectively, your channels are not, they don't always have to be for passing data. they can be used for scheduling by using the buffering and the queuing properties of the channel. I don't think that's really what channels were made for when they put them in here, but it's certainly a useful function case for them because it allows you to effectively, you see, with a wait group, if I start 10 functions and I tell it, okay, now wait for all 10 functions to be done, it's going to run all 10 in parallel. And if they run at different speeds, I've got to wait for all 10 to return before I continue. With this method, it's going to start the next one as one ends because the channel will clear. So effectively, this creates a situation where you're limiting your number of threads, but you're starting them as each thread ends. That makes sense. Okay, any other questions? Because what I'm going to do is we're going to call it for the week at this point. Later this week, I will paste this on the WhatsApp group and the Facebook group. I'm going to be taking everything we've covered up until this point, and I'm going to be creating kind of a mini exam, if I can call it that, because I need to judge where people are. And I'm going to ask people to get that back to me I'll probably post that by Monday, and I'll let people know when it's posted. If I can get that back by, say, Thursday, then when we start next week, because what I want to do from next week is I want to start actually writing some practical code to show you what you can now use all the stuff that you've learned to create. And we're going to create some APIs and maybe read some network data, etc., and take this into a more practical application. But to do that, I need to know where you guys are kind of sitting. So I'm going to put together some homework for you, which I'm going to post on Monday. And keep in mind that the more I know about where you are sitting and what you've learned, what you've struggled with, etc., the better I can help you as we move forward into the more practical aspects. So I would really encourage you guys to take that seriously and do it. Get it back to me. Ask me any questions, because once we move out of the kind of theoretical, here are all the different practical parts of this, into this is now real applications, I need to know that people are going to be able to follow it, and I can only help you follow it if I know where you're sitting. So does anybody have any questions about that or any thoughts on that, on me giving you homework?
I think it's a good sort of path for us to follow. And you are right. Before we go further, I think whatever has been covered until today, it would be sort of a good a revision to make sure that all the concepts are sort of understood when we actually do the things, and then we can proceed. Yeah, you have my vote for this.
Oh. Okay. Everybody happy then? Everybody okay? Any questions before we go about this or any of the previous content? By the way, I will be posting some channel demo code onto the GitHub repo in the next couple of hours, probably sometime this evening, my time. Okay. In that case, I think we're going to call it for the week. I hope I've managed to teach you guys something this week and you've enjoyed it. Thanks to everybody for joining and taking the time. It's much appreciated. And I will, as I said, I will post the stuff on the WhatsApp group as well as the Facebook group. And for those of you who are watching on YouTube, what I'm going to do is I'm going to paste the link to the Facebook channel where I'll post this because it's probably the easiest in the chat. And I'll also be posting it on my profile on LinkedIn so that you can find it there as well, just because I'm kind of multi-platform and equal opportunity. But yeah, thanks so much, guys. I hope you enjoyed it.
Andrew, thank you very much.
Thank you, Andrew.
Thank you, Andrew.
Cool. Thanks, guys. Cheers. Bye.